Welcome to today's webinar. I'm John Turpin, Product Line Application Engineer for the Tektronix Real-Time Spectrum Analyzers and Arbitrary Waveform Generators. Today we will focus on making radar measurements easy through the use of Tektronix Real-Time Spectrum Analyzers, Oscilloscopes, and Arbitrary Waveform Generators. I'll start by examining some of the easiest measurements to make, followed by the ever-increasing complexity of measurements required by modern radars. We'll see why even the simplest of measurements are difficult to make using traditional techniques and how this is made far easier with test equipment automation. Troubleshooting systems with real-time measurements and trend analysis will be covered, since problems that are discovered need to be analyzed further before they can be fixed. One way of making measurements easy is by unifying the user interface of the pulse measurements for oscilloscopes and spectrum analyzers. Next, we'll talk about receiver testing using arbitrary waveform generators and software such as the Tektronix RFXpress Signal Generation software, and touch briefly on system de-embedding. Testing any pulsed radar transmitter requires at least pulse width and pulse repetition interval measurements. Since these parameters are varied depending on the function of the radar, then testing these parameters is vital to the accuracy of the system. The time domain characteristics of a pulse naturally have their frequency domain equivalent. A narrow pulse has a broader spectral shape than a wider pulse. Similarly, a higher pulse repetition frequency or lower pulse repetition interval will have larger spaces between the spectral line components than a slow pulse repetition frequency. Using a traditional spectrum analyzer for these measurements, you might already be familiar with this phenomena. For the example shown here, the frequency domain information can be translated back into time domain for measurements of pulse width, which is 1 over side lobe span, and the line spectra from the pulse repetition interval, which is 1 over the pulse repetition interval line span. To have correlated measurements of time and frequency, a measurement system must also have sufficient sample rate, bandwidth, and memory depth to fully characterize the signal. Manual measurements are sometimes used even today. A waveform is displayed on an oscilloscope, and the operator counts the divisions on screen or positions markers and cursors at appropriate points in the signal. When using a spectrum analyzer, one method is to measure the nulls in the spectrum, again using the graticule lines or markers. This can then be mathematically manipulated to determine the pulse timing parameters. Not an easy task. A spectrum analyzer can also be used in zero-span mode. This operates like a high-quality RF detector followed by an oscilloscope. By using compute power, automated baseband pulse measurement routines have been added to the oscilloscope, but while these measurement routines work very well on baseband pulses, they do not perform as well with RF modulated pulses, since the oscilloscope must trigger individual cycles of the RF burst, identifying the exact time domain measurement points, such as 50% rise and fall positions, is very difficult. What I've done here is I've put together some demonstration signals that I would normally be using for a live demo, but in this media I think I'm just going to stay with the static screenshots. What I'm showing here is a very simple CW pulse radar. You would start off with a carrier frequency which goes through a pulse shaper, finally to an amplifier, and then the antenna. What a clean signal looks like is all the pulses are all the same, have the same rising and falling edges. But an impaired signal, the rising and falling edges have a severe amount of jitter. As we saw previously, the effects of pulse width and PRI can not only be seen in the time domain, but the frequency domain as well. On the signal on the left, you can see the clean signal with several very clear spectral lines. On the right, you can see the impaired signal. In this case, we've lost a lot of dynamic range because PRI is changing so drastically. We'll see these signals again later on in the presentation as we make measurements with other kinds of tools. What you can see here is a traditional way of making RF measurements. We're going to make spurious and harmonic measurements on this pulse, but only during the duration of the pulse. On the left side, you can see that the power versus time measurement straddles the rising edge. That would cause the measurement to splatter in the frequency domain, not giving you a very good dynamic range for the measurement. Instead of that, we offset that power versus time marker so that it now straddles the first stable part of the pulse. Next, we'll decrease the RBW so that we can maximize the length of time that we're measuring the signal and also maximize dynamic range. When you increase the length of the measurement in the time domain, you decrease the resolution bandwidth in the frequency domain, and vice versa. So by decreasing the resolution bandwidth, we get a longer time record. On the right-hand side, you see that now we have a nice signal with really good dynamic range. Now we can make RF measurements just over that part of the pulse. Since the real-time spectrum analyzer has a limited bandwidth, 165 megahertz on some models, if we want to see a wider frequency range, we have to step the instrument through each step of 165 megahertz. That also means that we have to trigger on the same pulse that we were triggering on in the first band. As you can see here, by telling it to trigger on each step across the frequency band, we can see all of the spurs and all of the harmonics that are produced by that fundamental signal. Okay, so it seems easy so far. While these measurements are relatively straightforward and easy to make with a little help from the test equipment, modern radars produce much more than a steady stream of equal pulses. Modulating pulses for pulse compression, varying the PRI to eliminate range gate blind spots, and other variations in the pulse sequence are now used to transmit the minimum power necessary and yet still be able to receive the greatly attenuated return signals. CW radars are also used for low probability of intercept applications in very cluttered environments such as automotive collision avoidance radars. These types of radar can employ combinations of linear frequency modulation and nonlinear frequency modulation or chirping, frequency hopping, and phase coding on carriers that are transmitted and received continuously. Since some measurements are more properly made in the time domain and others in the frequency domain, it is necessary for radar testing to be performed in both. Frequency domain tests include spurious signals, which can be caused from many parts of a radar system, including DSP and control software, and even the hardware itself. Spectrum measurements of the transmitted signal and spectrum power measurements of the assigned channel and adjacent channels also need to be made. These are all done in the frequency domain. Single pulse timing measurements reveal the quality of individual pulses. Width, pulse repetition interval, rise and fall times, and modulation errors are some of the more common measurements. Measurements of multiple pulses shows difference between individual pulses that can cause false or blurred radar readings. The first step in measuring radar pulses is actually detecting them and then parameterizing them such that all of the measurements can be made on a common pulse model. Once this model has been determined, parameters for each pulse can be measured. Sometimes the model itself is used to make these measurements. Some of these measurements can be made with that model are rise time, fall time, pulse repetition interval, and pulse width. Statistics can then be applied to calculate the variation of the entire ensemble of pulses. The pulse-to-pulse trend, histogram, and even frequency domain analysis can be applied to highlight potential problems in the radar system. Here is a closer view of the pulse model. The model is constructed with 4 cardinal points and 4 lines. These points and lines are the fundamental form from which all of the measurements are referenced. These lines, line rise 1 and 2, line fall 1, line top, and line bottom, are first defined. These lines are the result of a reiterative least squares fit designed to minimize the errors between the acquisition points and the resultant lines. The best fit process begins with an estimate of the top line. 50% of the points along the top of the waveform are used. These points are taken from the center of the pulse and determine the slope of the top of the waveform. Similar lines are drawn for the rise time, and a least squares fit is performed, adjusting each of the lines to minimize error. The intersection of these lines, the cardinal points, shown in green on the diagram, define a transition from rise to fall to line top. All measurements are performed based on these points. For example, the T-on time is defined as a period between the intersection points of the line top. Finding a pulse can be algorithm intensive, especially if testing is performed over a wide amplitude range. When the pulses are at a lower power, noise makes the determination of the cardinal points difficult. The basic trade-off between the various detection algorithms is the reliability of detection versus the speed of the algorithm. Even though the pulse measurements are an offline process, as in they only operate on data already stored in memory, the user still wants the measurements to complete as fast as possible. The method used in the advanced pulse analysis includes 4 separate pulse detection algorithms. Each of these algorithms is called within the DSP processor one at a time. They are called in order of the simplest and fastest first. Then the next detector with increasing complexity will be tried. This will continue, and if any time a pulse is found, then the process ends. This method allows the pulse and its amplitude to be found as accurately as possible in the least amount of time. As an example of an instrument which contains these built-in algorithms, the various Tektronix RSA models provide many tools to characterize transmitter designs. New statistics such as pulse trending and histogram allow the designer to understand pulse parameter variations. New measurements such as IPR, impulse response, and delta frequency are now bring the total number of measurements calculated on every pulse to 28. While the built-in measurements provide accurate metrics, some defects are best visualized using specialized real-time displays. In this screenshot, the larger LFM chirp pulse can easily be seen, as well as left to right, a lower power CW pulse, 2 even lower power LFM chirps, and 3 other pulse signals. Looking further at other visualization tools, amplitude, frequency, and phase versus time can be used to visualize many artifacts that are not readily apparent in the frequency domain view. For example, the frequency versus time display shows an up chirp, an up-down chirp, and a modulated chirp. The phase versus time view shows the same signal with all 3 pulse types providing a different phase curvature. Once a signal artifact is detected visually, triggering can be used to isolate it so further analysis can be made. On an oscilloscope, triggering is typically applied so that the signal can be stabilized on screen. For long signal acquisitions, triggering is also used to use acquisition memory more frequently. This is especially true for pulsed RF signals since the off time is rarely used and yet is almost always a majority of the signal playback time. For more complex signal effects, more trigger types are always better. Frequency mask trigger acts as a user-defined monitor for multiple frequencies. Time-qualified triggering provides a way to trigger on events of a specific user-defined duration. Trigger input and output signals can synchronize multiple instruments together using all of these triggers. New triggers such as frequency edge trigger are also very useful and not only trigger the time domain real-time measurements, but also all of the measurements in the instrument. The RSA models have 4 real-time processes. The real-time capture, similar to VSAs that we previously spoke about. DPx, which captures, processes, and displays up to 390,000 or more DFTs per second in histogram format. Spectral density trigger. You can draw a box over a signal of interest in the DPx display and trigger on its spectral density when the signal occurs again. Frequency mask trigger. As I said before, you draw your own mask and make it look anywhere in the span for signals of whatever amplitude you've designed the mask for. Conversion of trend data into the frequency domain allows for easy viewing of the nature of the modulation and therefore revealing key information about its source. The spectral view can show if the modulation is a single frequency or if several frequencies are included. The RSA enables this capability by performing a fast Fourier transform on the trend measurement results. On the left side, you can see that the amplitude is changing at a particular rate, which looks somewhat sinusoidal. And so we take those points We run an FFT over those, and we can see that there's a 4 kilohertz modulation. This is not the incoming power, but more likely a switching supply inside of the radar. Going back to our demo signals, this time I changed to a linear frequency modulated pulse. It's the same width as the other pulses we were looking at, but this time I've got a couple of other things happening here. So if we trigger with using power trigger, that's very popular for pulse measurements, just looking at the rising edge, then what we see there is we see that we've got a lot of jitter in the falling edge, a very excessive amount of jitter, probably unrealistic in any of today's systems. What we see on the right is we've taken a signal from a time base on the transmitter that we know is exactly at the PRI and should be aligned with the rising edge on every single pulse. So now what we can see, we see that both the rising and falling edges jitter by about the same amount. We'll look at that a little bit closer now. Further analyzing the signal, we also see that if we just use a power trigger, we see that the slope is got a lot of noise in it, what appears to be noise. So there's a lot of vertical displacement of the frequency ramp. If we trigger with external trigger using the time base, so we know exactly when the pulse is supposed to be happening, we can see that in the center of the pulse, it's very clean. It's actually right where it's supposed to be in frequency, but the ends extend a little bit farther. The way an LFM chirp is sometimes made is the baseband chirp generator goes in through a mixer, and then you do the pulse shaping or the envelope shaping of the signal. So what this is starting to look like, it's starting to look like the baseband chirp generator is all right, but the pulse shaper is the thing that's jittering on us. Looking at this signal one more time, we're going to look at the phase versus time performance of the signal. Again, on the left side, we're doing a power trigger on the rising edge of the signal. And this is showing a parabolic shape in phase, which is what you would expect for a linear frequency modulated chirp. If we trigger on the external trigger on the time base, now we see that the phase parabolas are all lined up, even though they are shifted. Adding oscilloscopes back into the picture, trade-offs can be made between acquisition bandwidth, dynamic range, and cost. Modern oscilloscopes can capture more than 30 gigahertz of bandwidth, which can then be processed by an extra set of software. The goal is to keep the user interface similar enough that essentially you only need to swap out the hardware. Tektronix real-time spectrum analyzers all include radar options for the base RSA software. Performance oscilloscopes have signal view options, which add radar and many more measurements to the oscilloscope, all with the same user interface. Multi-domain oscilloscopes can be used with Signal View PC, using the MDO to acquire data and automatically pass it to the software, which runs on a PC. The MDO is not only a lower cost solution, but also adds more triggering options to the measurement system. Logic triggering on the MDO, for example, can synchronize logic events with RF waveform captures. We're going to look at our demo signals one more time. This time we're going to use the automated pulse measurements to measure those same parameters that we were seeing visually on the other measurements. On the left we see the clean signal, as you can also see in the DPx display, and you can see the pulse measurements. They show that the PRI is very stable all the way across. This is for 128 pulses. We're measuring the PRI versus pulse and displaying it in the upper left window of the left diagram. On the right-hand side, you can see the impaired signal, and you can see how much PRI variation there is from pulse to pulse. Looking at the same signal, but this time looking at the pulse width variations, we can see that the clean signal has very low variation in pulse width. On the right, you can see the impaired signal, and it also has very low variation in pulse width. From this, we can infer that not only is the rising edge jittering and the falling edge jittering, but they're also jittering together, which keeps the pulse width the same. Turning to signal generation for a moment. Transmitter stimulus testing is often used to select components such as up-converters, amplifiers, and linearizers. A signal generator can also be used as a block substitution for the actual radar for applications such as radar cross-section analysis. Receiver validation is important not only to test sensitivity, but also blocking and selectivity that might be anticipated from common interference sources. Receiver functionality can also be performed for scene generation, such as target recognition in the presence of common countermeasures or clutter. Test tools need to be flexible to test at the available test access point, digital or analog, and at baseband I and Q, IF, RF, or microwave frequencies. In addition to synthesizing known signals, the flexibility to import waveforms from common DSP tools such as MATLAB and/or replay captured waveforms for acquisition tools like spectrum analyzers and oscilloscopes must also be considered. When designing, testing, and maintaining complex radar receivers, a flexible and accurate signal source is required. The Tektronix RFXpress Signal Generation Tool makes the signal creation process easy. Precise amounts of impairments, such as noise and interferers, can be added to test the robustness of the receiver design. One example of a signal that you can make with RFXpress is a radar signal that from the receiver's standpoint is coming from a sweeping antenna. You can set the scan rate and the beam pattern to standard patterns such as linear array or pencil beam. Just as software can make radar analysis easy, software can also make radar signal generation easy. This picture shows the Tektronix RFXpress application software being used to create Barker-coded and frequency-hopped radar pulses. Within minutes, you can create many types of radar signals that are then directly synthesized by the AWG. The lower left is an example of a Barker code with the measured frequency versus time plot shown on the spectrum analyzer. The lower right shows the frequency versus time overview, spectrogram, and DPx spectrum of the same synthesized frequency-hopped signal. Another example of a common test signal generation pattern is the creation of staggered PRI pulses, target velocities that correspond to multiple integers of the PRF are referred to as blind speeds. This terminology is used since a multiple target indicator filter response is equal to 0 at these values. Blind speeds can pose serious problems on the performance of MTI radars and their ability to form adequate target detection. Using PRF agility, by changing the pulse repetition interval between consecutive pulses, can extend the first blind speed to tolerable values. Another important part of receiver testing on radar systems is to make sure the receiver can work well in a noisy environment. The RFXpress Signal Generation Tool allows you to create signals such as 3GPP, GSM, CW radars, Wi-Fi, WiMAX, and also any of the other signals that you can make with the modulation software that is also part of RFXpress. So here we're looking at a simplified radar system in development. All of the different pieces are in development at the same time, typically. Although the team could wait until final integration to verify that everything plays together nicely, testing earlier in the process is obviously less risky. By substituting flexible test equipment for sections of the radar design, many of the other radar sections can be tested with reasonable certainty of interoperability with those sections that are not yet designed. This is also called de-embedding. In this situation, it is often useful to record the actual signals for later analysis. These recordings can be in length of hours, days, or even weeks. A de-embedded receiver, such as the instrument shown here, needs to be able to stream the data at full rate to an external baseband recorder. So in summary, modern radar systems require advanced automated measurement techniques. Many triggering modes are required for characterizing and troubleshooting systems. The more, the better. Advanced signal acquisition methods, such as fast frame, streamed recording, triggering are required to see the whole picture. Time correlation of measurements with a test instrument and between multiple instruments is also required for system-wide troubleshooting. Rapid changing signals require test instruments that are designed for real-time acquisition and processing. Unifying the user interface among a variety of test instruments allows easy translation of test processes among wide and ultra-wide, performance and mid-range, time domain and frequency domain instruments. Thank you for your time in listening to this webinar. More detailed information can be found for Tektronix-specific solutions in our application notes, such as fundamentals of radar measurements, generating advanced radar signals using arbitrary waveform generators, and other documents. These can all be found on www.tektronix.com/radar. Thank you again. This is John Turpin at Tektronix.